Well, in chapter 7 we introduce eigenvalue eigenvector problems, and these problems have applications for the solution of differential equations. Okay, so it will be used in the associated course of state space control, but it will also be used in the course in the second semester, Dynamique des systèmes mécaniques. We'll talk about positive definite matrices, and this concept we'll use also in the course of state space control, but in the course of optimization as well. And then we'll talk about singular value decomposition. We'll skip the subsection on similar matrices. In this course we have put a lot of emphasis on the system of equations ax is equal to b, and in general it comes from steady state problems. Well, let us illustrate this. In the second part of the course on state space control, we come up with a state space model of a linear system, and it has this form over here. Well, I'm not going to go into the details, but there are n states describing your system. So this is a vector that has dimension. It's a column vector, n times 1. Obviously, its derivative will also have dimensions n times 1. So A here is an n by n matrix. Okay, U, well, that's the input. In general, there will be m inputs, so U will be a vector with m inputs, so it's m times 1. So in order to be compatible, you immediately see that B must be n times m. Okay, so suppose that we have U that is constant, and we'll denote it UC here, and we are interested in the steady state solution. What will be x if U is a constant? Well, then you know that x dot will be 0, and you end up with the system ax is equal to minus buc, and this one we can rewrite as b. Okay, and indeed this is a system of the type ax is equal to b, and it's associated with the steady state problem. Okay, we are interested in the solution when x is constant, okay, for a constant input. Well, with eigenvalues and associated eigenvectors, we'll be able to look at the dynamics of this system, because we know that the solution of this will be something that will be changing with time. Okay, so elimination will no longer be useful. It's useful for the steady state problem, but not to describe the dynamics, and we'll be using eigenvalues and eigenvectors. Well, it's easier to explain eigenvalues by starting with the eigenvectors. Okay, so you know that in general, if you take a vector x and you look at ax, well, ax will not be in the same direction as x, but there are some vectors which are a bit special, and they are such that AV, okay, AV is in the same direction as V, and those vectors are called the eigenvectors of A. Okay, so multiply an eigenvector by A, well, the resulting AV is the original vector, okay, multiplied by the eigenvalue. So you have this thing over here, okay, and obviously the product AV is in the same direction as V. Well, remember that the equation that is underlying eigenvalue and eigenvector problems is this one. AV is lambda V. So you take the image of V by the matrix A and you have a vector that is parallel. Okay, they might not be collinear, the length might have changed, but they are parallel. You can rewrite this equation differently. Okay, so AV is equal to lambda. You put an identity matrix over here, and then we bring everything on the same side and we use associativity, and you end up with this equation over here, which is this one over here. Okay, obviously when you look at this equation here, there's a trivial solution, V is equal to 0, but we are looking for non-trivial solutions. Okay, so there will be non-trivial solutions for this equation if this matrix here has dependent columns. So if this matrix is singular for the given value of lambda. Okay, so if this matrix is singular for the given value of lambda, this means that its determinant must be 0. Okay, so by writing this determinant we obtain the so-called characteristic equation and we can recognize the eigenvalues. Okay, another way of looking at this equation over here, or this one, is that you say that the eigenvector, okay, associated to the eigenvalue is in the null space of this particular matrix over here. Okay, once you've isolated the eigenvalue, okay, it's in solution of this equation over here, you can solve for the associated eigenvector by solving this equation over here. So if a matrix has a 0 eigenvalue, okay, well, this equation over here becomes this equation over here. Okay, and this can only be true if the matrix is singular. Well, lambda is an eigenvalue of A if and only if this matrix is singular. Okay, and we know that a matrix is singular if its determinant is 0. Okay, so we can write this equation here, which we will call the characteristic equation, find all the solutions, which we call the roots, and these will be the eigenvalues of A. Once we have all the solutions, okay, for a given lambda I, okay, for a given eigenvalue, you can find the associated eigenvector. Okay, and this one you can obtain by solving this equation in which you have injected the corresponding eigenvalue. Well, first maybe a little trick that you can use to check your results when you compute eigenvalues and eigenvectors. It's always good to check your results, and it's true for a matrix that is square and that is in Rn times n. You will have eigenvalues, and we'll call them lambda 1 up to lambda n. Okay, well, the sum, okay, of all the lambda I is equal to the trace of A, and the trace of a matrix is the sum of the diagonal elements. Okay, you can also take the product of the lambda I, and this will be the determinant of A, and this comes in handy to check in general for any matrix. Okay, so you have computed the eigenvalues, check if these two properties hold. If it's not the case, you have made a mistake in the computation of the eigenvalues. But it's particularly handy for cases where A is in R2 times 2, okay, because you have two eigenvalues and you have two conditions, okay, so you can simply find the eigenvalues using these two equations over here. Okay, so let's talk a little bit about elimination, okay, and I want to tell you that eigenvalues are not preserved when you do elimination. Okay, let's do a simple example. Let's take this matrix here. It's very easy to obtain the eigenvalues. This matrix is singular. You can see that the column 2 is 3 times column 1. So you immediately know that there is an eigenvalue that is 0. And you know that the sum of the eigenvalues must be the trace, and the trace is 7 over here. So the second eigenvalue must be 7. Okay, so let's do elimination on this one. It's pretty easy, right? So we have got here the pivot. Okay, so we have to do this kind of operation with a multiplier that is 2. Okay, and this will lead to this matrix over here. Okay, obviously it will have an eigenvalue which is 0, but the other eigenvalue must be 1. Okay, you know that the sum of the eigenvalues is the trace. The trace is 1 over here, so the second eigenvalue is 1. So you see that when you do elimination on a matrix, well, the eigenvalues are not preserved. Well, in this first example, we consider a so-called Markov matrix. Okay, and in a Markov matrix, well, the sum of the elements in a column will add up to 1, as you can see. Markov matrices, they are used in so-called hidden Markov models. So, before I talk about the hidden Markov model, as you can see here, I'm on the Wikipedia page of the hidden Markov model. We'll talk a little bit about the state space model. That is the topic of the second part of the course on state space control. And such a model can be described by a differential state equation. I've introduced this one before. Okay, so this is the state equation, and there is also an output equation that takes this form. This is an output equation, and it's a static equation. Basically, what you need in control problems is the state of the system. Sometimes this state is not available. It's not available for measurements. The only signals that you can measure are the outputs y. So the idea is, can we obtain an estimate, okay, of x based on the measurements y? Well, the hidden Markov model are probabilistic in nature. Okay, so again, there is a state, okay, and there is kind of an observation. Okay, and I will explain this using this very simple example that I've drawn from this Wikipedia page. Okay, so the state here, well, it's either rainy or sunny, and there is a transition probability. For instance, if it's rainy, well, you have a 70% chance that it's rainy tomorrow, and of course a 30% chance that it's sunny tomorrow. If it's sunny, okay, then you have a 40% chance that it's rainy tomorrow, and of course a 60% chance that it's sunny tomorrow. So this explains the Markov model or matrix. You would have here 0.7, 0.3, 0.4 and 0.6, and this is why the entries of the columns add up to 1. Okay, this transition probability, you can see it over here. So there is also a measurement, and it's called the emission probability. And here the emission probability says, well, our friend Bob over here, if it's rainy, well, you have a 10% chance that he will go walking, 40% chance that he will go shopping, and a 50% chance that he will go cleaning. If it's sunny, well, there's a 60% chance that he goes walking, 30% chance that he goes shopping, and 10% chance that he goes cleaning. Okay, this is what you can see over here. Okay, and remember this estimation problem that you had in the state space case. Well, for the hidden Markov model, there are also estimation problems. Can we, using a sequence of events of what has happened over a number of days, estimate what the state has been in those days? Okay, so it's kind of a similar problem, but in an other framework, a more probabilistic framework. And as I said, the applications are pattern recognition. Okay, so let's return to our Markov matrix and compute eigenvalues and eigenvectors. So for the eigenvalues, we need to consider the determinant of A minus lambda I. I here is a identity matrix. Okay, so we are looking for the solutions of this equation over here, and if we compute the determinant, we've got this over here. Okay, and if we factor, we obtain this, and the two roots are 1 and a half. So lambda 1 is equal to 1 and lambda 2 is equal to a half. And by the way, for a Markov matrix, the eigenvalues will be such that the biggest one is always 1 and the other ones are smaller than 1. Okay, so now we can compute the associated eigenvectors. So we need to look for vectors that are in the null space of this matrix for lambda 1 and lambda 2, and this leads to two systems of equations. Here we'll find the eigenvector of lambda 1 and here the eigenvector of lambda 2. Okay, this one is v1 over here and this is v2 over here. So how do you solve this? Well, usually you put one of the entries to 1. So let's take the second one over here. We put this one to 1 and you immediately see that you have to put the second entry to -1. So here is the eigenvector v2 associated to lambda 2. You can do the same thing for v1. So what you could do is put the second entry sorry, to 1, and then you see that you have to take 1.5 for the first entry. So that's an eigenvector. But you can immediately see that if v1 is an eigenvector, so av1 is equal to lambda v1. Okay, so if you multiply by k, which is a scalar over here, okay, you can also see that k v1 is also an eigenvector. Okay, so here we have taken an eigenvector that is like that, but you see that the ratio of the two elements is 1.5. So this is also a valid eigenvector. We have chosen it like this because we want the sum of the two elements to be 1. So I have skipped 2 pages or 2 slides on the Markov matrix, and this Markov matrix has well, certain properties, and if you're interested, well, you can have a look in the slides. What I'm showing you here is the interpretation of the eigenvalue eigenvectors, okay, and it is best shown in Matlab using a command that is called eigshow. So this is what I will show you now. Okay, so I've got some code over here that I want to show you, and you can see over here that I have this command eigshow that I will be using. This command is available up to Matlab 2016. After Matlab 2016 it's no longer available, but it's not a problem. You can do something quite similar yourself by a little bit of code. I like this because, well, it gives you kind of an animation, and I will show you. Also, the eigenvalues and eigenvectors of a matrix can be obtained using the command eig in Matlab. The eigenvalues will be here on the diagonal of this diagonal matrix, and the eigenvectors will be stacked in V over here. Okay, so if we run this, I've got two figures, but I just want to show you V. Okay, these are the eigenvectors, but they are not exactly the ones that are in the slides because they have been normalized. Okay, so if you take the length and the norm of the first column, you will see that it's 1. Okay, and it's the same thing for the second column. Okay, and indeed you will indeed find the eigenvalues which were 1 and 0.5. So this is what is shown using eigshow, and this is what is obtained using the second figure. Okay, so what is nice about eigshow is that I can take x, and x will be here on a circle, and I can look at the image of x through a. Okay, so in green you have the vector x, and in blue you have ax. Okay, and if I start turning this, in green I will have, as you can see, a circle, and have the image of the circle in blue. Okay, and in certain directions you see that ax and x are kind of aligned, so it must be somewhere here. This means that this direction is an eigenvector. Okay, so this is eigenvector 1, and it corresponds to the eigenvalue lambda 1 is equal to 1. So I keep on turning. I see that there is a second eigenvector. This is the eigenvector 2, and the corresponding eigenvalue is a half, as you can see. Well, you can find the same interpretation in the 3x3 case, but there is no appropriate command here in Matlab 2019, and anyway this command would not work for 3x3 matrices, so you have to write your own code. This is what I've done here. So over here you can see this is the code I'm highlighting now. It's the code to produce a sphere of radius 1 using cylindrical coordinates. So this is the matrix that we are considering. It has eigenvalues 2, 0.5 and 1 with associated eigenvectors, and now we can have a look at the image of the sphere through 8, and we can use, well, the mesh function to represent all this in 3D. Right, and we'll consider different views, and in each of these views you will see two of the eigenvalues corresponding to, well, corresponding eigenvectors. Okay, so we can run this. So over here we can see the eigenvalue 1, here eigenvalue 2. Over here it's eigenvalue 1 and eigenvalue 0.5. And here you have the eigenvalue 2 again, and here the eigenvalue 0.5. Okay, So we can also have a look how this looks like when we turn. Okay, so this is in purple the image of the sphere through this matrix A. Well, let us look at the following projection matrix. Remember that a projection matrix is A times A transpose divided by A transpose A, but because we have used a unit vector, this one is 1 over here. Okay, so if we are projecting on A, this is how it looks like. So let's take a reference frame and let us say this is A over here. Well, for this case, it's quite easy to know what the eigenvalues and eigenvectors are, because of course there is one vector that will be projected on itself. Okay, that's the vector A. Okay, so one eigenvector will be A, right? And the associated eigenvalue will be lambda equals 1. Okay, and it's quite obvious that a vector that is perpendicular to A, okay, well, it will be mapped on the origin, okay, and the associated lambda will be 0. Okay, so one eigenvector, the other eigenvector will be perpendicular. Okay, so this vector is indeed perpendicular to V1 is equal to A. Okay, and the associated lambda is equal to 0. Well, there are other ways to see that the eigenvalues are 1 and 0. This is a singular matrix, so of course you know that there is one lambda is equal to 0. Then you could say the trace is 1, so we know the other eigenvalue. But you could also say, well, this is a Markov matrix, so we know that it must have a eigenvalue that is 1. Well, I've got the same code here with this eigshow command here for the projection matrix. Let's have a look. Okay, so I can now start turning as we said. Well, this is the direction of the vector on which we project. Okay, so if we project the vector on itself, obviously we have lambda is equal to 1, which is an eigenvalue. Okay, and in this case we have considered here a vector that is perpendicular to the vector on which we project, so lambda 2 is equal to 0. Okay, so the circle here has been mapped to a very or an infinitely thin ellipse. Okay, and the eigenvalues are 1 and 0. So this is here a reflection matrix, and we have been talking about this reflection matrix because it's an orthogonal matrix. So remember that we are considering reflection across a line that is perpendicular to u. So if this is u over here, the line that is perpendicular is over here. Okay, so every x is reflected across the 45-degree line. Okay, so again, it's easy to obtain eigenvalues and eigenvectors. Suppose that we take a vector that is along this line here, it will be projected on itself. So obviously lambda 1 will be equal to 1, and well, this corresponds to an eigenvector that is perpendicular to u. So let's take the unit vector that is perpendicular to u and we'll denote it like this, right? So now if we take a vector that is on the direction of u, okay, for instance the vector u itself, this one will be mapped to this vector over here. So it will have the same length and it will be in the opposite direction. So we see here that the eigenvalue must be -1 and the associated eigenvector, if we take the one that is of unit length, will be u itself. Okay, so two eigenvalues, 1 and -1. This is also a permutation matrix. Okay, it's an identity matrix 2 by 2 where row 1 and row 2 have been interchanged, and permutation matrices are such that their eigenvalues are either 1 or -1. Another way to obtain the eigenvalues is to see that the trace is 0, so the sum of the eigenvalues is 0 and the determinant is -1, so their product must be -1. So the only solution is lambda 1 is equal to 1 and lambda 2 is equal to -1. So we can have a look at this visually for this reflection and permutation matrix using Eigshow. This is what we obtain. So I can play with the vector x and look at its image, and indeed when x is in the direction that is perpendicular to u, we see that ax and x, they match, so lambda is equal to lambda 1 is equal to 1. And when x is in the direction of u, we see that ax is in the opposite direction. But apart from that, it has the same length, so lambda 2 is equal to -1. So we can look at this rotation matrix, which corresponds to a rotation matrix where theta is equal to 90 degrees. So we rotate everything with 90 degrees by multiplication with q. Okay, we can compute the eigenvalues, so you need to take q minus lambda I determinant, and this is minus lambda minus 1 minus lambda, and we have to take the determinant, so this leads to lambda square plus 1 is equal to 0, and we see that the eigenvalues are complex, they are not real, and the corresponding eigenvectors you can compute them and they are complex as well. This is also kind of logical, right? Because you would not expect when you multiply by the matrix Q to find vectors that are in the same direction, okay? Because of course they are all rotated by 90 degrees, and this is what we'll see when we consider the Eigshow command. So let's have a look. So we see here x and the multiplication by ax, and without a surprise, well, x has been rotated by 90 degrees, okay? So if we keep on turning x, well, its image ax will always be at an angle of 90 degrees, okay? So we clearly see that it's not possible to have real eigenvalues. So we've seen that multiplication of an eigenvector by a matrix A is very simple. It's just you take the vector and you multiply by the corresponding eigenvalue. So it is very easy and all difficulties are swept away. So this is what we'll try to do. We'll follow eigenvectors separately. And if you do this properly, and if you use the eigenvectors properly, in many problems you can turn the matrix A into a diagonal matrix lambda. And this is what we'll discuss next. Well, suppose a matrix A n by n has n eigenvalues, lambda 1, lambda 2 up to lambda n, with associated eigenvectors v1 to vn that are linearly independent. Then you can construct an eigenvector matrix S by simply stacking the eigenvectors one next to the other. Okay, so this leads to this matrix over here. And since the eigenvectors are linearly independent, well, S minus 1 is defined. So S is a regular matrix. It has an inverse. Well, for this matrix here, with linearly independent eigenvectors, you can construct the matrix S minus 1AS, where S is the eigenvector matrix, and this matrix will be a diagonal matrix with the eigenvalues on the diagonal. This is called diagonalisation. Well, this can be proven quite easily. Remember the product AB, if we use the column interpretation, can be written as A times the first column of B. Okay, the second column is A times, well, the second column of B. And of course you have to continue up to the last column. Okay, so this is what we'll be using twice. So I'm looking at AS over here. So S is this matrix over here. We have stacked the eigenvectors. Okay, so I'm now using this column interpretation. So the first column will be A V1, but we know that we have eigenvalues and eigenvectors. So in general, A Vi here is lambda I Vi, where I is equal from 1 to n. Okay, A times, and the second column will be A times the second column, so we'll have AV2 here, and the last column will be A Vn, and this is equal to lambda n Vn. Okay, so we've just proven that A times S is this matrix over here. We've rewritten this matrix over here, and you can show that it is the matrix S times the matrix lambda. Okay, so indeed, if we divide this in columns, the product S times lambda will be the matrix S times the first column of lambda, but that will be, of course, just lambda 1 V1. Don't forget that S times the first column of lambda is a linear combination of the columns of S using the coefficient. So what we'll do here is select lambda 1 V1. So here we have lambda 1 V1, and you can do the same thing here for the last column. The last column will be S times the last column of lambda, and by doing that you'll select lambda n Vn, and this is exactly what you've got. So this is equal to S times lambda. Okay, so this is what we've shown over here. But the matrix S has an inverse, and because we know that all eigenvectors are independent, so if you pre-multiply by S minus 1, you've got this over here, or if you post multiply, you can write A in terms of lambda and the matrix S. Well, let's do an example with this simple triangular matrix. Well, the trace of A is equal to 7, and the determinant of A is equal to 6. Okay, so the sum of the eigenvalues is 7 and their product is 6, so we find that lambda 1 is equal to 1 and lambda 2 is equal to 6. We find the eigenvectors by considering the problem AVI is equal to lambda I vi, or equivalently A minus lambda I times the identity matrix times vi is equal to 0. Okay, so this is what we obtain here for lambda 1 is equal to 1, and this is what we obtain for lambda 2 is equal to 6. So usually what you do is set one of the entries to 1. So let's put this one here to 1, and then you see that the other one has to be 0. Okay, so we find one eigenvector. We do the same, we put this one to 1, and we see that we have to put the other one to 1 as well, and this leads to the second eigenvector. Okay, so we had this relation, s minus 1 as is equal to lambda. So this is my A matrix. Here you see that you've got v1, and here you've got v2. Okay, so now we need to compute S, and this is something that you should be able to do. So it's 1 over the determinant. The determinant is 1. And then what you do is you interchange these two over here. Okay, and you have to change sign over here. Okay, so this leads to this matrix over here. When you compute a 2 by 2 inverse, please check and multiply s minus 1 and s, and obviously they would give you the identity matrix. Okay, so if you do the calculations, and please do, you'll obtain a diagonal matrix with the eigenvalues on the diagonal. So in the previous slide we had done an example where s minus 1 as is equal to lambda. Okay, and s was 1101, a was equal to 1506, and s minus 1 was equal to 1 minus 101. Okay, this is equivalent to saying that, well, here it's not A, of course, it's lambda. Okay, so it's a diagonal matrix, and in this case lambda was equal to the eigenvalues 1, 6. Okay, so this is equivalent to saying A is equal to S lambda s minus 1. Okay, this allows us to compute powers of k. Okay, so you have to consider A multiplying itself several times, and each time what you've got here is s minus 1s, and this is the identity matrix. So a power of A, the power k of A, is s times the power k of lambda s minus 1. Okay, taking this power of lambda is quite easy. Okay, so A to the power k here is s, you've got it over here, this is s lambda k. You're multiplying diagonal matrices several times, okay, and s minus 1. Okay, and this simply leads to this matrix here, lambda k. It's the diagonal element to the power k, and then you can multiply and you obtain here A to the power k with k that can be any integer. Okay, so you can see obviously that you obtain A when you take k is equal to 1. Okay, you obtain the identity matrix with k is equal to 0, and you even obtain the inverse for k is equal to minus 1. This is a matrix that is very important for the description of state space models after they've been discretized. So suppose that the eigenvalues of the matrix are all different, then the associated eigenvectors are automatically linearly independent, and this means that the associated matrix can be brought into a diagonal form. This is something we want to prove. So suppose we have two eigenvalues that are different, and we assume that the eigenvectors are linked by this equation over here. So what we'll do with this equation, first we'll multiply it by a to the left. A v1 is lambda 1 v1 and a v2 is lambda 2 v2. Secondly, we take this equation and we multiply it by lambda 2. This will lead to this equation here, and now we take the difference. Okay, so this term will cancel out and we have this equation over here. We have assumed that lambda 1 and lambda 2 are different, so this is different from 0, so this means that C1 is equal to 0. If we do the same thing but we multiply the equation by lambda 1, you can prove that C2 is equal to 0. Okay, so this means that the only linear combinations of the eigenvector to produce the 0 vector is the trivial combination C1 equals 0 and C2 equals 0. So V1 and V2 are linearly independent. Okay, so we have proven it here for a 2 by 2 matrix, but the idea extends to n eigenvectors. When A has repeated eigenvalues, it is not necessarily diagonalizable. Diagonalisability depends on the null space of the matrices A minus lambda I associated to the repeated eigenvalues. So can you find an eigenvector for each of the eigenvalues? So we can multiply eigenvectors by non-zero constants. So if V is an eigenvector, kv is also an eigenvector with k different from 0. Okay, so here remember, in this case over here we had two eigenvectors. We had an eigenvector 1 0, and this is v1, and v2 was equal to 1 1. Okay, so what we have done over here, we have multiplied the first eigenvector by k1, different from 0, and the second one by k2, different from 0. This leads to s, and if we compute s minus 1, you'll obtain this here. And if you do the computation of s minus 1 as, well, you obtain a lambda again. Okay, so this dependence on k1 and k2 disappears from s and s minus 1. Well, the eigenvectors in S come in the same order as the eigenvalues in lambda. So what we've done over here is written S, and we've put the second eigenvector first and then the first eigenvector. And what has happened in lambda is that we have obtained here lambda 2 and here lambda 1. Okay, so you have the eigenvalues in the same order as the eigenvectors. Well, there is no link between invertibility, does the matrix have an inverse, and diagonalisability, can it be brought into a diagonal form. Invertibility is concerned with the eigenvalues being 0 or not. You know that if there is an eigenvalue that is 0, the matrix does not have an inverse. Diagonalisability is concerned with the eigenvectors. Is there an eigenvector for each eigenvalue? Then you can ask the question about the power ak, okay, where k is increasing, okay, and the question is, when is this power going to go to a zero matrix? Well, it's going to go to a zero matrix if all eigenvalues are smaller than 1 in absolute value. So here we take a matrix that is parameterized by the coefficient k over here, and we look if it is diagonalizable or not. It's an upper triangular matrix. Okay, so we can compute the eigenvalues by computing the determinant of a minus lambda I. So this is a minus lambda I, and I've chosen an example with a triangular matrix because now it is easy to obtain the characteristic polynomial, right? It's just the product of the elements on the diagonal. Okay, you see that there is a double eigenvalue. Lambda 1 is equal to lambda 2 is equal to 1, and there is the third eigenvalue that is 2. Okay, so let's just have a look at the eigenvector associated to lambda 3 is equal to 2, and we have to solve this equation over here. So v3 here, v3 is v3 1, v3 2, and v3 3. So what we have done over here is simply impose that v33 is 1. The second equation leads to minus v32 plus 3 times v33 is equal to 0. This one we have imposed it to be 1, so this leads to a 3 over here. The first equation is minus v31 plus k times v32, but v32 is 3, okay, plus 2 times v33, so v33 is 1, so plus 2 is equal to 0, so this leads to v31 is equal to 2 plus 3k. Okay, and this is indeed what we have over here. So this is the eigenvector v3 associated to lambda 3 is equal to 2. Okay, so remember we were considering a matrix A that was 1k 2 0 1 3 and 0 0 2. We had lambda 1 2 is equal to 1 and lambda 3 is equal to 2. So we're now looking at the eigenvector or vectors associated to this double eigenvalue, and we have to consider the problem A minus lambda 1 2 times the identity matrix times v1 2. Okay, so this leads to this eigenvector problem. So you can find one vector here which is 1 0 0, okay, in the case where k is different from 0. Okay, this is because the null space here has dimension 1. Okay, so you'll be able to find only one eigenvector that is such that this matrix times v is equal to 0. Okay, in this case the matrix is not diagonalizable. So suppose now k is equal to 0. Okay, well then things become different, and remember that we had k over here, and this is k is equal to 0. Now the null space has dimension 2. Okay, and it is possible to find two eigenvectors that are such that, well, this matrix times v is equal to 0. Indeed, you have this vector over here, but you also have this vector over here. Okay, remember that when k was different from 0, you only had the first one. When k is equal to 0, in this particular case, you can find a second eigenvector. Now, things are okay, right? Because you have two eigenvectors and two eigenvalues, okay? So you can construct the matrix S, compute S minus 1 AS, and indeed you'll find a diagonal matrix, okay? So our original matrix here, 1 K 2 0 1 3 0 0 2 has double eigenvalues, and it has a diagonalizable form only when k is equal to 0. Well, if we write the state space model in discrete time, we have something like this, and this is a difference equation. So if you take the homogeneous part, so if you put this one to 0, you end up with this equation over here. So if you start from x0, you have obviously x1 is equal to a times x0, x2 is a times x1, which is a square x0. So of course you end up with this equation over here. Okay, so if you write a as s lambda s minus 1 k times, you can write this like this. Remember that you'll always have here a s minus 1 s, which is the identity matrix. Okay, so you can write x0, the initial condition, as a linear combination of the eigenvectors of the matrix A, right? And this thing here, this is the same as writing x0 is s, which is v1 up to vn times c1 c2 up to cn. Okay, so this is s, this is c, so you have got s c over here. Okay, so if you plug that into this equation here, you know that of course c, that's written over here, is s minus 1 x0. Okay, so this is c over here. Okay, so xk is equal to s lambda k times c. Okay, this one is s minus 1 x0. So if we look in terms of matrices, xk, it's v1 up to vn, this is s. The diagonal matrix, it's lambda 1k up to lambda nk, and c is c1 up to cn. Okay, so this is how it looks like. Well, this one here, it's a times x, so it's a linear combination of the columns, and this thing here will be c1 lambda 1k in a vector up to cn lambda nk. Okay, and now it's this matrix over here, s again, up to vn, and this you can take the column interpretation, and this will lead to, well, what we have written over here. Okay, so the solution of this equation with initial condition x0, that is written as a linear combination of the eigenvectors, is obtained by this equation over here, and it's a sum of terms that involve, of course, the eigenvectors and the eigenvalues. Okay, suppose you want to find the solution of this difference equation, okay, with initial condition x0, and we'll assume that A has n distinct eigenvalues with corresponding eigenvectors vi. Well, you can find the solution of this equation. The first thing that you have to do is write the initial condition in terms of the eigenvectors as a linear combination of the eigenvectors. Okay, so this is the linear combination, and the solution is given by this equation here that involves the eigenvalues of A and the eigenvectors of A. This will be called the modes, or the discrete modes of the system, and this type of solution, well, we'll use it in the course Dynamique des systèmes mécaniques. So I will use the solution of this equation to compute the sequence of Fibonacci numbers. And the Fibonacci numbers are a sequence of numbers that you find in nature. They are interesting numbers, at least to my opinion, and we'll show that the ratio of two successive Fibonacci numbers tends to the golden number. This is given for your information, and if you're interested, you can have a look at these slides in the course, but I will skip these slides in this video presentation. Well, we have to compute the eigenvalues and eigenvectors of this matrix and bring A in a diagonal form. So let's first write the characteristic polynomial. 3 minus lambda 0 minus 2, 0 8 minus lambda 2, 0 minus 3, 1 minus lambda, and here it's a determinant. So oops, this is a matrix, and here it's a determinant. So we can construct the determinant by expanding on the first column, because we have two 0 elements over here. So this will give me 3 minus lambda. I don't have to change the signs because the indices are 1 1, sum is 2, it's even. So we have then to consider this determinant. It's 8 minus lambda times 1 minus lambda plus 6. This you can rewrite as 3 minus lambda. You have lambda square minus lambda minus 8 lambda, so it's minus 9 lambda plus 8 plus 6, so plus 14. Okay, so this you can factor here, lambda minus something and lambda minus something. Well, we'll have something where the sum of the coefficients here is 9 and the product 14, so this leaves us with 2 and 7. So the first eigenvalue is 2, the second eigenvalue is 3, and the third eigenvalue is 7. Okay, we now have to find the eigenvectors. Okay, so let's start with lambda 1 is equal to 2. So we are looking for a vector v1 such that this equation holds. So this will lead to 1, 0 minus 2, 0, 6, 2, and 0 minus 3 minus 1 times v1. So we'll write it as v11, v12, and v13 is equal to 0. Okay, we can, for instance, impose v11 to be 1, so the first equation here will give me v11 minus 2v12 is equal to 0. So this yields v12 is equal to a half, and the second equation over here, 6 times v12 plus 2 times v13 is equal to 0. That's a 1 over here. So here it's a v13. Sorry about that. So this is 1, and v12 is equal to minus 1 over 6. Okay, so what we can do to construct v1 is simply multiply everything by 6. So this leaves me with a 6 over here, a minus 1 over here, and a 3 over here. We remember that if v1 is an eigenvector, then k times v1 is also an eigenvector. So we've taken k is equal to 6 over here. So lambda 1 is equal to 3. This leads to the following system: 0, 0, minus 2, 0, 5, 2, 0, minus 3, minus 2, times v2, v2 1, v2 2, and v2 3 is equal to 0. So again we'll put v2 1 to 1, and it's easy to see that, for instance, the second equation will lead to v2 3 is equal to 0, and the second equation will then lead to v2 2 equal to 0. So we can take v2 equal to 1, 0, 0. Then we have our third eigenvalue. We have to solve the following system to find the associated eigenvector. Okay, so this is minus 4, 0, minus 2, 0, 1, 2, 0, minus 3, and here we'll have minus 6. Okay, let's again take v3 1 equals 1. The equation, the first equation will be minus 4 v3 1 minus 2 v3 3 is equal to 0. Now remember that this is minus 4, so v3 3 is equal to minus 2. The second equation will yield v3 2 plus 2 v3 3 is equal to 0. So this is minus 4, so v3 2 is equal to 4. Okay, so v3 over here is 1, 4, minus 2. Okay, so if we stack the vectors, this will be s minus 1. Then we need the matrix A over here. Then we just take s, and we should obtain lambda. Okay, so 6 minus 1, 3, 1, 0, 0, 1, 4, minus 2. We'll have something similar here. Here we have the matrix A. And then we have the matrix lambda. It's a diagonal matrix with the eigenvalues in the same order as the eigenvectors. Okay, so this is a diagonal matrix. So the off-diagonal elements are 0. Okay, so here we have diagonalized the matrix A. Well, you can check, of course, your response by multiplying s minus 1 as and see that indeed you obtain lambda. Well, there is another check that you can do, and we should have done this check earlier, right? It's that the sum of the eigenvalues, which is, well, 12, is equal to the trace of A, and the trace is indeed also 12. Okay, so this is something that you should use when you have computed your eigenvalues. Well, let's do a very similar example here, and I've already written the determinant that we have to compute and equal to 0. You can see that there are very few zeros, and if you just compute the determinant, you'll end up with a third order polynomials, and then you'll have to compute the roots, and this is, well, very difficult. So here you have to be a little bit smart in computing the, well, determinant. So this is why we know that there are rules for computing determinants and that you can create zeros. So if you replace R1 by R1 minus R2, okay, we won't change the value of the determinant, and we'll have 1 minus lambda, lambda minus 1, and 0 over here, 1, 2 minus lambda, 3, and here we'll have 3, 3, and 20 minus lambda. So now we can construct the determinant using the first row, and what we see here is that lambda minus 1 or 1 minus lambda, well, you will be able to factor it out. Okay, so you already know that one of the eigenvalues will be 1. So it's always a good idea to produce zeros and to maybe obtain a row or a column where you have the identical factors. In this case, it's 1 minus lambda. So let us construct the determinant based on this first row. So we'll have 1 minus lambda, and we'll factor it out. So we'll have 2 minus lambda times 20 minus lambda minus 9. And then we'll have this one with a minus sign, okay, because it's in position 1, 2, so it gives me 1 minus lambda if you change sign. And now we have to take the following determinant, so it's plus 20 minus lambda minus 9. Okay, so I'm not going to do the whole calculations, but if you do this, you'll obtain minus 23 lambda plus 42. Okay, but at least here we don't have a third order polynomial. We already have a factor over here, and this you can write as 1 minus lambda, lambda minus 2, and lambda minus 21. Okay, sum is 23 and product is 42. So we have lambda 1 is equal to 1, lambda 2 is equal to 2, and lambda 3 is equal to 21. Well, I've rewritten everything to give me some space, and now we'll look at the first eigenvector. So lambda 1 is equal to 1 over here, and we'll look at the problem minus lambda 1I times v1 is equal to 0. So this is equivalent to 1, 1, 3, 1, 1, 3, 3 319 times v11 v12 v13 is equal to 0. Okay, so there are not a lot of zeros here, so what we might do is maybe do row 2 is equal to row 2 minus row 1, and row 3 is equal to, well, row 3 minus 3 times row 1, and this will lead to the following system over here: 1 1 3 0 0 0, and here 0 0 10, v11 v12 v13 is equal to 0. So here we could, for instance, say that v11 is equal to 1. Then the third equation will lead to v13 is equal to 0, and the first equation will lead to v12 is equal to minus v11 is equal to minus 1. Okay, so the first eigenvector is 1 minus 1 0. So let us take the second eigenvalue, it's 2. So this leads to the system of equations 0 1 3 1 0 3 3 3 18, right? So I'm just plugging in lambda is equal to 2 in this over here, and this looks okay. So times v21 v22 and v23, so this is the vector v2 that we're looking for, is equal to 0 0. Okay, so when you look at the first equation, might be a good idea to take v23 is equal to 1. So the first equation will lead to v22 plus v23, 3 times v23 is equal to 0. So v22 is equal to minus 1, and the second equation will be v21 plus 3 times v23 is equal to 0, and this will lead to v21 is equal to minus 3, and it's the same equation, so of course this one should also be minus 3 over here. Okay, so v2 is equal to minus 3 minus 3 1, and let us take the third eigenvalue 21, and this will lead to the following system of equations. Okay, minus 19 1 3 1 minus 19 3 and 3 3 minus 1 times v31 v32 v33 is equal to 0. Okay, so what we can do over here is maybe do some row operations, okay, and produce zeros over here. So the multipliers will be minus 19 and 3, okay, and this will lead to the following equivalent system. So we'll produce zeros, and this can be seen as a pivot. Okay, So I will have minus 360 over here, 60 over here, minus 19, 3, 60, and minus 10, v31, v32, v33 is equal to 0. I can divide the equations here by 60, so this will leave me a 1, minus 6. I can do the same thing with 10 over here, so this will leave me minus 1, and this will leave me a 6 over here. So let's take v32 is equal to 1, and it will make it easy for the first equation. So we'll have minus 6 times v32 plus v33 is equal to 0. So v33 is equal to 6, and we'll take the second equation, and v31 will be 19 times v32 minus 3 times v33. This is a 1 over here, this is a 6, so this will lead to 1. So v3 is equal to, well, 1, 1, and 6 over here. Okay, so we can stack the vectors in S, and this will be 1 minus 1, 0, okay, minus 3, 1, and 1, 1, 6. Okay, and this allows us to write, well, S minus 1 A S is equal to lambda, and lambda will be, well, a diagonal matrix with the eigenvalues on the diagonal in the same order as the eigenvectors. So we will see later that in case a matrix is symmetric, and here it's indeed the case, you see that A is equal to A transpose. Well, you can work with a matrix Q, okay, and the matrix Q here, you have to take the eigenvectors and give them a unit length, okay. So in this case, this will be 1 over square root of 2 minus 1 over square root of 2, 0. This one will have 19, so minus 3 over square root of 19 minus 3 over square root of 19 and 1 over square root of 19. Okay, so its length is square root of 19, and this one will have a square root of 38 length. So 1 over square root of 38, 1 over square root of 38, and 6 over the square root of 38. And we'll see then that for symmetric matrices, instead of writing this, you can do something easier and write Q transpose A. Q is equal to lambda, the same lambda. You see that instead of having to take an inverse here, you can do a much simpler operation and just take the transpose. Well, here the matrix Q is orthogonal. Okay, so Q transpose Q is the identity matrix, and here we can use the fact that the matrix is symmetric to check your results. Okay, when we'll show this later in the theory, when the matrix is symmetric, well, then the eigenvectors are perpendicular, they are orthogonal. Okay, and you can see here that the scalar products v1 v2, v1 v3, v2 v3 are all 0. So obviously you can use that to check your results. And there is another check that we had forgotten again, and that we should do at the beginning of the exercise when we have computed the eigenvalues. Well, the sum of the eigenvalues here is 24, and indeed it corresponds to the trace. There is another check that you could do. The product should be equal to the determinant, but of course that is a check that will take much more time to verify.